Okay, chapter 7 looks at relations and functions. So the next 4 chapters actually look at relations and functions, graphing. So the graphing calculator that you guys were asked to purchase for this course really becomes a fundamental part of the next 4 chapters. Because instead of using table of values and graphing all of these by hand, what we will be doing is we'll be using the graphing calculator so that we can identify patterns and not worry so much about how to make the graph with a table of values, but what the graph looks like with equations for my table of values. So before we get started, we're going to get a little bit of a review of some of the important concepts. So we have the Cartesian coordinate system. So there was a French mathematician by the name of René Descartes, and in 1637 he suggested the idea of specifying the position of a point on a surface using 2 intersecting axes as measuring guides. So this Cartesian plane had a horizontal axis that we called the x-axis, a vertical axis which we call the y-axis. So the point of intersection of the 2 axes is called what? The origin. So the x and the y meet at the origin. On each axis, a unit length is chosen, and then everything's marked off. So we choose a scale. To specify a particular point on the grid, we use a unique ordered pair of numbers called coordinates. So in my ordered pair, which comes first? The x, and then y comes second. Alphabetical order, guys. X comes before y. X tells me which way to move. Horizontally, left or right, and y tells me to move up or down. So the point 4 and 3 is shown on the grid below. 4 over and 3 up, that's point P. So we can label it as point P being 4 and 3. If you notice, when I intersect my x and my y axis, I get 4 quadrants. The quadrants are numbered counterclockwise, and they are numbered using Roman numeral letters. So the first quadrant that we identify is the quadrant that we're most familiar with. It's the positive quadrant. The x's and the y's are both positive. So in quadrant 1, the x coordinate is positive and the y coordinate is positive. And that's how you can abbreviate positive, a plus sign with a VE. Okay. We're going to skip questions A, B, and C for a moment, and we're going to concentrate on D because it has to do with naming our quadrants. We start with quadrant 1 and we go counterclockwise. So the next quadrant would be this one. This would be quadrant 2. What can you tell me about the values of my x coordinates in quadrant 2? They are negative. And what are the y coordinates in quadrant 2? Positive. Again, moving counterclockwise, we now get into the bottom left-hand corner, which would be quadrant 3. And what can you tell me about the x coordinate in quadrant 3? It's negative. And the y coordinate is also negative. And then finally, quadrant 4. In Roman numerals, quadrant 4 is an I and a V because V represents 5, and the 1 or the I goes before it, so it's 1 before 5. That's how we get 4. So what is the x coordinate in quadrant 4? Positive. And the y coordinate? Good. Okay. So if I look at point A on my coordinate grid, what are the ordered pairs of point A? 2 and 4. What about B? Negative 3 and 0. So if I don't go up or down, it's 0. What about C?
6 and negative 3.
D.
0 and negative.
Thank you. And point O.
0 and 0.
0 and 0. What point lies in the second quadrant? E. And what are the coordinates of point E?
Negative 2 and 30.
Thank you. And what point lies in quadrant 3? F. And what are the coordinates of F? -3. Good. Okay. D and B do not actually belong to a particular quadrant because they are right on the axes. Okay? So what I'd like you to do is I'd like you to practice, or I'd like you to look at questions 1 and 2. So what we're going to look at first is we're going to use a pictorial pattern to describe a linear relation. So 3 toothpicks are used to form a triangle. A second triangle can be formed if I add 2 more toothpicks right here. And if I add 2 more toothpicks, I now get 3 triangles. So the next 2 diagrams in the pattern, I have 3 toothpicks, then I added 2 more, and then I added 2 more. So if I add 2 more toothpicks, that would be the next diagram in the pattern. And then if I did that again, and I added 2 more, that would be the 5th diagram in the pattern. So part B says complete the table relating the number of toothpicks to the number of triangles. So 1 triangle took 3 toothpicks. 2 triangles had how many toothpicks? 3 triangles? 4 triangles was, and 5 triangles was 11. So we're going to take this data and we're going to plot it. So when we go to plot something, we have our x and our y axes. T goes along the bottom. T is the number of triangles. So I need to label 1, 2, 3, 4, 5. I use a common scale, so I go up by 1s. I don't all of a sudden go up by 2s partway through. So I wouldn't go 1, 2, and then 4. If I'm going by 1s, it goes by 1s the whole way. And then going up the side is the number of toothpicks. I have to go up to 11. So I check. 3, 6, 9, 12. I could go up by 1s again. But I might not want to write all the numbers. So in this case, I could go 1, 3, 5, 7, 9, 11. I could label every second number because I am showing consistency. So 1 triangle, 3 toothpicks. 2 triangles, 5 toothpicks. 3 and 7, 4 and 9, 5 and 11. Now, should I join these points together?
Yes. Linear.
It's linear. So what would this point here represent? Can I have half a triangle? So does it make sense to connect the points? No. So the reason behind this, so why does it not make sense to join the points? Because the data is discrete. And I believe we looked at this term last year. We looked at discrete data and continuous data. This is discrete data. you can't have half a triangle. Or part of a toothpick for that matter. Either you have 7 toothpicks or you have 9 toothpicks. You can't actually draw a triangle in that pattern with 8 toothpicks. So part E says write or describe in words the relationship between the number of toothpicks and the number of triangles. So not going this way. We're not saying that the number of toothpicks increases by 2 each time. What I want to know is what's the relationship from the triangle to the toothpicks. So in other words, how can I go from 1 to 3, 2 to 5, 3 to 7, 4 to 9, 5 to 11? That's not describing in words though. That's a formula. So what you had there, you said 2x plus 1. Describe that in words. So what word can I use for 2?
Double the amount of triangles.
Okay. So double the number of triangles and increase by 1 to get number of toothpicks. So 4 triangles, I double it, I get 8, increase by 1, I get 9 toothpicks. So if we use an equation to represent this, I'm getting the number of toothpicks, which was P. So P is what I'm getting, so it's a P equals equation. I double the number of triangles, which again, the variable I was given was T, and then I add 1. That becomes the equation. So use the equation to determine the number of toothpicks if I have 27 triangles, because then I don't have to extend that table to 27. The number of toothpicks is double the number of triangles plus 1. So what's double of 27? Add 1. So I have 55 toothpicks. Use the equation to figure out how many triangles I would have if I have 83 toothpicks. So 83 is what I sub in or substitute in for P, and I'm solving for T. So we kind of review our solving equations. I want to get T by itself, so what do I get rid of first, the 2 or the 1? Subtract 1 from both sides. I don't necessarily need to show that I'm subtracting the 1, but when I subtract 1 on both sides, what am I left with? And when I divide by 2, what am I left with? So I have 41 triangles. Take a look at class example number 3 and graph the points that are listed in the table. So if we take a look at this one, if we represent the data on the grid, students in a physics classroom are determining the resistance in an electrical current by measuring the voltage when the amps are passed through the circuit. So if you remember when we talked about this in the past, my independent variable goes along here. That's the part in an experiment, it would be the manipulated variable. So what was I manipulating in the physics experiment? The amount of current that I passed through the circuit or the voltage? So go back and read this. The current. I'm manipulating the current and I'm seeing what voltage would come in. So current goes along the horizontal, voltage along the vertical.
Also, isn't it also like when you say input output?
Yes.
Scan.
So what's my input? The input is the amps, the output is the volts. So now I need to come up with a suitable scale. I only need it to go up to 4 amps. And if I look here, I've kind of got these darker lines. I could use that and I could make my graph bigger. I've got this much grid room, I might as well use it. 1, 2, 3, 4 amps. So I could put that this is I measured in amps. And then the V is measured in volts. And I need to be able to go up to 48. So what would be a suitable scale to go up by? Tenths. Which means each of these little markers is how much? 2. 2, 4, 6, 8, and then I get to 10. So I've got half an amp, which is going to be right in the middle between these two, and 6 volts. And then I have 1.5 amps, and I have 18 volts. 3 amps gives me 36 volts. 3.5 amps, 42 volts. And 4 amps was 48 volts. Could I join these points together?
Yeah.
Why?
Because you can have a partial.
Fractions.
Yeah, fractions.
Yeah. Because measuring amps is a continuous measurement, and so is volts. I could have 2 amps. So if I join from this point here, and I use a ruler, it makes a straight line. And if you notice, that straight line goes through what point? What do we call this?
Origin.
The origin. Does it make sense that 0 amps is going to have 0 volts? Yep. Okay. So it says, use the graph to determine the voltage for a current of 2.5 amps. So 2.5 amps would be right here. So I'd follow this up to this, to where it hits the line, and then I'd follow it across to get how many volts? 30 volts. Okay. Anyone come up with an equation that I can use? If I gave you the number of amps, could you tell me how many volts there would be? So looking at the relationship between the numbers. So in other words, what could I do these numbers to get? So in my case, when I look at this, I always look at the whole numbers. What could I do to 3 to get to 36? Multiply it by 12, and then I check to see, does that work for 4 times 12? What about half times 12? It's equal to 6. 1.5 times 12, it's equal to 18. So I start off with the numbers that are easier. I don't need to necessarily start off with the front of my display or my table of values. So an equation to determine volts, or express volts in terms of amps, volts would be 12 times the amps. So when I have 6.2 amps, how many volts would I have? What'd you get, Tyrone?
74.4.
And what do I put after that? V for volts. Resistance is calculated from the equation V equals I times R, where I is the amps, V is the volts, and then R is the resistance. State the resistance in this electrical circuit. So I pick known values. .48 volts was 4 amps. And then the resistance is what I'm solving for. What does R equal? 12. So the resistance is the same as what I got up here. So resistance is 12 ohms. What's the symbol for ohms?
It's omega.
Right? So these two questions, class example 3 and class example 2, talked about continuous and discrete data. So if you flip to the next page, it outlines discrete and continuous data again. In class example number 3, the variables I and V are examples of continuous variable because they can take on every value within a particular interval. In other words, that's what IE stands for. A variable for which it is possible to find an intermediate value between any two values. Or in other words, in the case of our example, the current could be anything from 0 to 5 amps. So it could be 1.2 amps. It could be 3.0001 amps. The only thing limiting me would be the measuring or the tools that I have. In class example number 2, P and T, the number of toothpicks and the number of triangles, could only take on limited values, whole numbers, and therefore they're not continuous. These are called discrete variables. When you are graphing these, discrete variables are unconnected dots or unconnected points, whereas discrete data can be joined by a straight line. Now, sometimes you might actually join discrete data with a straight line if you were looking for values on that, and if your numbers, if your scale of axis was quite small. So I think we did a question last semester with, or last year, that had to do with a dance, the amount of money that you would make in a dance compared to the number of tickets. Well, if I'm selling 500 tickets, to have to put 500 dots on my graph would just seem kind of ridiculous, and they'd be so close together. So in that case, I may want to join the points together. Classify each of the following as being discrete or continuous. The time taken to complete a 100-meter sprint. Continuous. Because it is possible to have 3.2 seconds or 9.856 seconds. Again, the only thing that's the limiting factor is the measuring tool itself. The number of students who pass Math 10. That's discrete. I can't have half a student pass the course.
Well, you could try.
I can try, it's just not going to work.
We do try everything.
The height of students. Continuous. Again, my limiting factor would be my measuring tool. And what about shoe size? Discrete. Shoe size, not foot length, shoe size. So shoe size is discrete because, again, we don't have, like, you're either size 7, 7.5, or 8. You're not a 7 3/4 shoe. They don't come in 7 3/4. They don't come in 5 5/8. It's
I'm gonna
either.
start making shoes.
You're going to start making shoes like that? Good luck. Okay, so I gave you questions 1 and 2. I want you to now do question number 5 to 12.